Part 2, I/O, atoms, and operators. In this section, we'll cover the most basic Python elements. First, we'll learn how to receive input and send output from our program. Next, we'll look at the basic data structures, most of which are atomic. That is, they should be treated as whole entities. Finally, we'll see how to act on atomic data structures through the use of operators. By the end of this section, you should be able to know how to receive input to and send output from a Python program, identify the integer, floating point, Boolean, and string atomic types, and know which operations apply to each atomic data type. So let's start with an example. We're going to whet your appetite by solving quadratic equations. So a quadratic equation is one of the form shown on your screen, which has got two solutions given by the equation that's shown there. The value of b squared minus 4ac is called the discriminant and is used to decide whether a solution is real or imaginary. We would like to calculate the value of the discriminant. Here's how we would do this. I/O in Python. Programs do not run in total isolation. They have side effects. They need to receive input and send output to the outside world. Otherwise, they would not be very useful. For every program, the outside world may refer to the operating system in which the program lives, or the console program where we run our program. In this part, we learn how to produce these side effects through the use of two intuitive functions. Print sends input to the console. Input reads input from the keyboard. The simplest program we can write simply sends text back to the console, that it has only output. The next simplest program receives some input and returns it to the output. So here we slightly modify it by including the input in a string. So far so good, but hardly useful. To do more useful things with programs, we need to expand the range of things we can represent. We do this by employing various data types. Data types allow us to represent objects in the real world. Atomic data types. In order to represent different kinds of data, Python provides 5 main atomic data types: integers, floating points, booleans, strings, and none. Let's look at each of these in turn. Numerical data can either be whole numbers or fractional numbers, that is with a decimal point. We refer to the former, the whole numbers, as integers, and the latter, with decimal point, as floating point numbers. Both of these may either be positive, negative, or 0. Integers are represented by the int data type and are used to express discrete quantities. Floating point numbers are represented by the float data type and are used to capture fractional values. Logical data are represented by Booleans through the bool data type and are used to capture the results of Boolean algebra. There are 2 possible values for bool, true and false. Textual data representing arbitrary sequences of literal characters, that is characters for writing, are represented in Python by strings using the str data type. A Python string can capture any language and is technically referred to as a Unicode string. Strings are defined by content bounded by quotation marks, which take several forms: single, double, or triple quoted strings. The triple quotes, either with 3 single or 3 double quotation marks, allow you to include quotation marks within strings. Python provides a special data type called the none type for empty or none value. And there's only one value for this called none. We'll see how none is used in part 4. So here's your first task. Create a new project with a Python module structured in the standard format you were introduced in part 1. Inside the main, print out an example of each of the types above. Operators. Now that we have a way of representing data, we need a way of expressing interactions between data items. This is done through operations expressed by operators. Each type of data, each data type is subject to a set of operations. It is easy to understand operations and operators through familiar symbolic representations. For example, numerical data, integers and floating point, allow the operations of addition, subtraction, through the use of the corresponding familiar arithmetic operators, plus, minus, multiply, and divide operators. The last two are not provided directly by computer keyboards, so when writing programs, we substitute them for the asterisk operator and the forward slash respectively. Therefore, we can naturally express mathematical operations on numbers using this or these operators. In the last example, we have included parentheses to group operations that should occur together, as we would in arithmetic. So here's a task for you. Continuing with your previous task, now perform the above operations using operators and view the results. Boolean operations can similarly be performed on Booleans, resulting in Boolean values, true or false. The main operations are conjunction, and, choice, or, and negation, not. Again, parentheses are a handy way of expressing how some of the operations have precedence over others. That is, which operations should be performed first. So here's a task for you. Repeat the previous task for Booleans. Can you predict what the results will be before you run the module? The none type does not allow any operations, but can be evaluated for Boolean values. We'll see examples of this when we get to the section on constructs. Strings are a much richer data type and allow plenty of operations such as concatenation, joining multiple strings, extension, as well as other handy ways to embed values into them through the f-string representation that we have already seen before. Most of the operations of strings are performed through methods, which are functions attached to the string object. To call a method, we simply add a dot immediately, followed by the method name, and pass any required arguments. You can see the full list of Python string methods from the link provided in the instruction manual. Here are some examples. Later on, we'll see how to also treat strings as containers using the in keyword, and how we can do some indexing and other operations of characters. So here's a task for you. Run the previous tasks for string operations in your module like the previous tasks. Using the string methods provided in the Python documentation, there's a link provided in the instruction manual, experiment with several methods to see how they work. What interesting things can you do with them? Variables, representing values symbolically. Recall from earlier when we introduced input and output, we had the name variable. We used name to capture the user's input, which was assigned using the assignment operator. Any part of an expression that occurs on the left side of the assignment operator is called a variable. Variables are handy ways to give some data a name. Every subsequent use of the variable will refer to this data. There are a few rules of thumb when deciding on variable names. These rules apply also when naming functions and classes. The full convention is described in PEP 8 and it's a link provided in your instruction manual. Do not use built-in function names like list, dict, sorted, and so on. Otherwise, the functionality they refer to will no longer be available. You can find a list of built-ins in the official documentation page, and there's a link in your instruction manual. To avoid ambiguity, never use L, lowercase l, O, uppercase letter O, or I, uppercase letter I, as single character variable names. To create variables resembling keywords or built-in functions, include a leading or trailing underscore. For example, if you want to use from under or under from. Import is replaced with either import under or under import, etc. Try to avoid idiosyncratic abbreviations. Instead, use legible words separated by underscores for readability. Instead of RTT underscore MSK, use rotate mask. Instead of RSLT, use reserved, and so on. Good variable names should begin with a letter, which is A to Z, upper or lowercase, or an underscore. As you grow in your knowledge, you'll find that Python code tends to use a permissive convention of defining variables, functions, and methods to start with a lowercase letter. Function argument names are also lowercase. Classes begin with an uppercase or a single underscore followed by an uppercase. Global variables are all uppercase, for example, listed in the instruction manual. Python is a dynamically typed programming language. This means that once we define a variable as one type, we can change it to refer to another type without any special instructions. This is both a strength and a weakness of Python. Let us now put together what we have learned about data types, operators, assignment, and variables by applying it to a simple arithmetic equation. So consider the following equation: y is equals to 2x to the power 4 plus 3. In mathematics, x and y are similarly named variables. Their values can change. Y is referred to as a dependent variable because it depends on x. That is, changing x results in a corresponding change in y. In Python, we can express this relation as follows, because our program will compute values of y given x. What remains is a way to assign a value to x to complete the program. Suppose we assigned a fixed value to x, say x is equals to 12.3. We now have a complete program which we can run. So it's a task for you. Write out a new module, give it a fitting name, for example, calculating or calculate_y.py. Then using the above lines of code to complete it to view the value of y. Now the above program has a fixed value of x, which is not very useful. We can make it more useful by asking the user for input using the input function as we did before. So here's a task. Write out your program using the input function, but it fails. Paying special attention to the last line of the error, what reason does Python give? Debugging. Now let's take a short tour to understand Python errors and how to fix them. No one writes perfect code the first time. The more ambitious our programs, the more likely we are to introduce unintended errors. These errors are referred to as bugs, and the process of exposing and amending them is referred to as debugging. Whenever a Python program fails, it prints out a stack trace or a traceback. The traceback is like a map showing you the sequence of function calls the program took up to the point of failure. This can get quite lengthy, and being able to understand what a traceback is telling you is an essential skill. In running the last program, you should have seen something like this. The last line classifies the type of error. In this case, it's a type error. The stack trace tells us the following key pieces of information. The classification of the error. Here we have a type error, meaning that we may have performed an operation that is inconsistent with the types involved. The detail of the error tells us that the exponential operator or double asterisk or pow operation failed because we used incompatible types, a string and an integer. The module where the error occurred, main.py. The line in the module where the error occurred. For this, we look at the lowest line beginning with the file. Here it is line 5. PyCharm provides this as a link that we can simply click to get our cursor to the right place. Python provides a multi-purpose function called type, which can help us debug what exactly went wrong by inspecting the data type of a variable. We use it by passing to it the variable of interest. So here's a task for you. Print the output of the type function for x immediately after it is assigned a value. What is the type of x? What do we need it to be? Coercion or casting. We've seen the basic types: integers, floating points, booleans, and strings. Corresponding to each of these are functions: int, float, bool, and str, which we can use to create corresponding types from appropriate types. Once we know what type we want, we can coerce or force an appropriate value into that type using the special functions. A simpler way to write above is to combine the coercion and the assignment in one operation. And now we can run our program again. And here's a task for you. Why did we use float data type? What will happen if we use int for the equation above? Similarly, we can cast between types as long as the value is appropriate, and so on. So here are the key takeaways: that you now have enough knowledge to write simple Python programs that can solve arithmetic operations. We've only just scratched the surface. There are many other operators that you can perform on numeric types. Visit the official documentation to see a whole host of them and play with them to see what they can do. There's a link provided in the instruction manual. Remember to also give the string methods a try. There are a ton of them, and there's a link provided in the instruction manual right at this point. So you can check your progress by going back to the instruction manual. There's a set of multiple choice questions that you should follow along just to test that you've understood the basic ideas. And there are 4 challenges, excellent challenges for you to extend the problem by being able to actually solve quadratic equations. So now we're going to use everything we've done so far and extend it step by step until you're able to do that.